In this video, we're going to demonstrate how one might go about analyzing a mass spectrum for an unknown. Now, what I've given here in this picture is a picture of a mass spectrum that you might be given as part of this lab. And so what we'll do is we'll go through this mass spectrum and analyze it and see if we can come up with a molecular structure for a molecule that would have given rise to a structure like a mass spectrum like this. Now, there's a couple of things that we can get immediately from looking at this diagram. First and foremost, and you really need to learn this, is that the highest peak, that is the highest mass peak here, represents the molecular weight of the compound. So already, without doing any work really, we know that the molecular weight of our compound must be 52. That's the highest mass peak. There's another thing that we can get by immediately looking at this diagram, and it's a little bit subtle, but I think it's easy to see. Okay, I have a big mass peak here at 51. How do I get a mass of 51 if the whole molecule is 52? Remember that every peak that we see in this spectrum represents a fragment of the whole molecule that we're dealing with. All right, so if a peak at 51 up here would necessarily represent a mass of a fragment that's missing one atomic unit. So in this case, a mass of 51 would be our molecule minus a hydrogen. Okay, so if our molecule is minus a hydrogen, that must mean there must be, this mass of 51 represents the loss of one hydrogen. The mass of 50 here must be the loss of a second hydrogen. So we know right off the bat that there are two hydrogens in our molecule. Okay, so with two hydrogens in our molecule, that means that all of the heavy atoms must add up to 50. So the question is, how can we get to a mass of 50 using our list of possible isotopes? Now, I've listed them here, and these are the ones that are given in the lab handout so that you can see what our possibilities are. So we need to find some combination of all of these heavy elements that adds up to 50. All right, now I want to show you another shortcut that one can take that will make this a little bit easier. And one is that our lowest mass down here is 12. Okay, there aren't very many ways we can get a mass of 12 except for having carbon. So what we have here is a carbon atom that represents this mass of 12. So what we're really looking for are some other masses that add up to 38, because if I take 50, which is the 52 minus 2 of the hydrogens, and subtract 12 from it, I'm going to get 38. And so 38 is the mass of the other heavy atoms in this molecule. So how can we get to 38? Well, I could start off with sulfur, and I've got 32, so I must have 6 more added onto that, but there's no way I can get a 6. So this one can't work. I could also start with phosphorus, which is 31, and add 7, but again, I can't get that to work. I could also start with silicon and add up to 10, but I don't have a mass of 10 among these isotopes, so that doesn't work. So I can already eliminate all 3 of these elements. They do not appear in my compound. Okay, but I get down to fluorine. Now fluorine, I could have 19 plus 19. Well, I could have 2 fluorines in here, and that would equal 38. All right, okay, what about oxygen? Okay, if I have oxygen, then I have a leftover mass of 32, so I'd have 22, so I'd have 16 plus 22, but there's no way I can really get a mass of 22. And I'll invite you to try that with all of this list of isotopes. There's no way you can put 2 atoms together and add up to 22. So oxygen is out also. All right, similarly, if I have nitrogen, okay, so if I have nitrogen, then I have a mass of 14, which means that I am adding to that a mass of 24. Okay, but 24 could be 2 carbons, so I could actually construct this as 14 plus 12 plus 12, and then I would have a total mass then of 38 coming from that. Okay, so I have a couple of possibilities here. I have a possibility of having 2 fluorines, or I have a possibility of having a nitrogen with 2 carbons to add up to those 38 mass units that I'm missing. All right, so which one is more likely? All right, I'll just point out that if I start trying to construct a Lewis diagram that has, now it's got to have a total of 3 carbons. So let's put this down here, 3 carbons plus a nitrogen plus 2 hydrogens. So I have a total molecular formula of C3NH2. I can try all I want, but I'm going to have a hard time putting together a good Lewis structure that includes this set of atoms. And part of the problem is that I want my carbons to each have 4 bonds, I want the nitrogen to have 3 bonds, and I want each hydrogen to have 2 bonds. And it just turns out there's no way I can put those together to make a Lewis structure that works. So in fact, I'm going to be able to eliminate this possibility simply based on the fact that these things don't work together. Okay, but what about the other one? Okay, I've got a carbon, I've got 2 hydrogens, and I have 2 fluorines. Does that work to make a molecule? Well, I can imagine drawing a Lewis structure that looks something like this. I've got a hydrogen, a fluorine, and a fluorine. And I haven't drawn this very carefully here, but you get the idea. What I'm going to have is basically a methane type molecule that's got 2 fluorines substituted for hydrogens. All right, so this is my leading candidate for the molecule that would make this mass spectrum here. But how can I make this, how can I be assured that this is the case? All right, well, one way I can do it is to see if I can construct each of these masses using a fragment from this molecule. Well, suppose I lose a fluorine atom. Okay, so if I start with breaking this bond here, then I would end up with a CH2F fragment and a fluorine. Okay, well, the CH2F would have a mass of 14 plus 19, which would be 33. Well, gosh, that looks a lot like that peak right there. And then it also has 2 hydrogens attached to it, which is consistent with what I'm seeing down here in this part of the spectrum. Okay, I also have a mass at 19, which tells me there's a fluorine. So, in fact, that would be very consistent with this particular structure. All right, what about other fragments I could make? Well, I could break the second fluorine off, and then I have a mass of 14. Well, I do indeed have a mass at 14. It's very small, and it also is indicative of having a CH2 group put together here. So, in fact, what I can demonstrate is that this particular assignment, to say CH2F2, is a good possibility for the molecule that made this mass spectrum. All right, it matches all of the masses that I have. It has 2 hydrogens, which is consistent with the fragmentation pattern. It has 2 fluorines that is also consistent with a difference in mass from here to here. Okay, if I lose a fluorine, I go from 52 to 33. So all of this together gives me good confidence that this is, in fact, the interpretation of this mass spectrum.